Okay, so now we're going to talk about rock, paper, scissors. First, we'll write out the payoff matrix for it, and then we'll try and find a mixed strategy Nash equilibrium. Okay, so okay, you guys remember rock, paper, scissors. You have three actions available. So rock, paper, and scissors. Okay. Um, Rock crushes scissors, paper covers rock, and scissors cuts paper. So rock's going to beat scissors, paper's going to beat rocks, and scissors will beat papers. When you play this game, it's a two-player game, so let's do P2 here, P1 here, and the actions available to them. Suppose they play this game just once until you have a single payoff matrix. If both players choose the same action, so let's say both of them choose rock, then you have a 0, 0. With papers, you have 0, 0, 0, 0. Right? That's just a tie. But we know that rock beats scissors, so this is a 1, this is a -1. Rock beats scissors, so this is a 1, and this is a -1. Paper beats rock, so paper covers rock, so this is a 1, -1, -1, 1, and scissors cuts paper. So 1, comma, -1, -1, comma, 1. As always, you write the payoff of player 1 first, then the payoff of player 2. Let's look at best responses. If player 2 chooses rock, you want to choose paper. Player 2 chooses paper. Player 1 wants to choose scissors. Player 2 chooses scissors. Player 1 wants to choose rock. If player 1 chooses rock, player 2 wants to choose papers. If player 1 chooses papers, player 2 wants to choose scissors. If player 1 chooses scissors, player 2 wants to choose rock. Right? There's no action profile that is stable here, which means that there's no Nash equilibrium in pure strategies. So my set of pure strategy Nash equilibrium is the null set. Okay, this is the empty set or the null set. Means there's nothing there. But if I go back to hmm, if I go back to result number 5, my action sets here are finite, rock, papers, and scissors. I have a finite number of players, that's just 2, and I have a symmetric game. And I defined a symmetric game a few videos ago. That must mean that there exists a symmetric mixed strategy Nash equilibrium. So a symmetric mixed strategy Nash equilibrium is one in which both players choose rock with the same probability, both players choose paper with the same probability, and both players choose scissors with the same probability. So that must mean that if I assign a probability P R P P P S here, Q R Q P Q S here, then in a symmetric mixed strategy Nash equilibrium, PR star has to equal QR star. PS star has to equal QS star. And the P star has to equal QP star in a symmetric. And we are guaranteed that one exists because this game is symmetric. It's symmetric because both players have the same action sets. So A1 equals A2, and that's just the set rock, paper, scissors. And because ui of x comma y equals uj of y comma x. Let me write it in terms of 1 and 2. u1 of x comma y equals u2 of y comma x for all x, y. Right, so player 1 of rock, so this is reflected by this is reflected by this is reflected by this, and so on. Right, what does reflection mean? It means that what player 1 earns when player 1 chooses S and player 2 chooses R, so U1 of S R, should be reflected by what player 2 earns when player 1 chooses R and player 2 chooses S. Right, and because each of those payoffs is reflected along this negative 45-degree line that I drew here, this dotted line, because of that reflection, this is a symmetric game, which means that a symmetric MSNE must exist. Okay. This just follows result 5. Okay. Now, I want to make one more assumption, and then we'll go about solving this. And I want to assume that each action is chosen with positive probability in equilibrium. We can solve this without that assumption, but that assumption just makes life a bit easier. So it's like we're going to guess and verify. We're going to guess that in our symmetric mixed strategy Nash equilibrium, each action is chosen with positive probability, and then we'll verify that later. We can also just do this without that assumption, but I want to be lazy, therefore I am being lazy. Okay, what's our steps to finding equilibrium? So let's say I want you to find the MSNE that satisfies the properties that I gave earlier, so that it's symmetric and that each action is chosen with positive probability in equilibrium. Okay. First thing we need is expected utilities. So EU1 from rock given the vector Q should equal something. EU1 from paper given the vector Q should equal something. EU1 from scissors given Q should equal something. And Q, I assume, is the vector QR, QP, QS. Right, so taking that as given, what is the utility that player 1 gets from choosing R, P, and S respectively? From choosing R, player 1 will get this 0 with the probability QR, -1 with probability QP, and 1 with probability QS. So that's just QS minus QP. From choosing paper, player 1 will get 1 with the probability QR, 0 with probability QP, -1 with probability QS. So that is QP minus QS. no, sorry, QR minus QS. And then from choosing scissors, that one gets -1 with probability QR, 1 with probability QP, 0 with probability QS. So that is QP minus QR. Okay. Now, if each action is chosen with positive probability in equilibrium, then each of these terms has to be equal. Right? Because if player one is choosing R with positive probability, if player one is choosing P with positive probability, if player one is choosing S with positive probability, then player one's expected utility from rock has to equal player one's expected utility from paper, has to equal player one's expected utility from scissors. Right? So I'm using this assumption that I made here, and I'm combining that with the result 6, which says that if in equilibrium there are two actions, each of which is chosen with positive probability, then it must be that the expected utility that player one gets from choosing the action AI has to equal the expected utility that player one gets from choosing that other action, right? So AI here can be rock, AI prime can be paper, or AI can be paper and AI prime can be scissors, and so on. Okay. Going back here, what this tells me is that QS minus QP has to equal QR minus QS, which means that 2 times QS minus QP has to equal QR. So first I just added QS on both sides. Now I'm going to add QP on both sides. 2QS equals QR plus QP, or QS equals QR plus QP divided by 2. Right, this is just algebra. So I set these two things equal to each other first. Now I will just set these two things equal to each other, the next two lines. So it has to also be that QR minus QS has to equal QP minus QR. Okay, let's add QR on both sides. So that becomes 2 times QR minus QS equals QP. Let's subtract QP from both sides. So that's 2QR minus QS minus QP equals 0. And now let's add QS on both sides. So we get 2QR minus QP equals QS. But from earlier, we know that QS is also equal to QR plus QP divided by 2. Let's multiply both sides by 2. Add 2 times QP on both sides. Subtract QR from both sides. Okay. And then QS, which is QR plus QP by 2, will also equal QR, which will also equal QP. Right? So they're all equal in equilibrium. And because they're simple probabilities, we know that QR plus QP plus QS has to equal 1, which means that QR star equals QS star equals Q star. Right? Because that's the only way they're equal to each other and add up to 1. Each of them has to be 1/3. And because the equilibrium that exists here, the mixed strategy Nash equilibrium, is symmetric, it also has to be that P R star equals Q R star equals 1/3. P S star equals QS star equals 1/3 and P star. If this is because of symmetry. And so this is our mixed strategy Nash equilibrium. Right? A mixed strategy Nash equilibrium is just a profile of probability distributions over actions. And so this is a very intuitive result here where it's a perfectly symmetric game. You rock, paper, scissors. And in equilibrium, you find that each player is choosing each action with a probability 1/3. So this is 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. Okay. Good. I'm going to pause here for now. And I think this is all I'll do with you guys online. And then I'll continue on September 9th in person. All right. Cheers. Please make sure to watch these videos. If you have any questions, please do ask me. If not on email right now, then later on in person on September 9th. All right. See you guys.